nuclei.
Thank you, Sonia, and thank you to all the organizers for inviting me here to give a presentation on couple cluster calculations of deformed nuclei. So first of all, I'd like to just thank all my collaborators and young people and postdocs who has been involved in this work, who are all highlighted here in boldface. And also you'll hear a nice talk coming after my talk here by Francesca, who will talk about couple cluster calculations and the different applications to response functions. So just to set the context a little bit here, this is from a workshop we had a couple of weeks ago in Saclay discussing the role of pairing in nuclei and the apparent lack of pairing from chiral EFT interactions. So we know that pairing has a tremendous impact on rotational or collective structure of nuclei. So this is shown here for heavy deformed nuclei. So you have this rigid rotor limit here, and if you compare with experiment where you extract the moment of inertia, you see there is about a factor of 2 smaller moment of inertia than it was expected from this rigid rotor model. So the impact of the superfluid phase here, or the rotational flow, really impacts this kind of rotational structure and extractive moment of inertia here. And so once you include that in a, let's say, this cranking model here, you see you nicely reproduce data. So we know that superfluidity from this data here reduces the moment of inertia. Also, there's something called rotational stretching, and this is from a EFT model of my collaborator here, Thomas Pappenbrock and Eduardo Cola Perez. About a decade now, they've developed effective field theory for deformed nuclei. And what is known from data is that the higher spin states or rotational band has a larger moment in inertia than what is expected from this simple leading order formula here. And so in effective field theory, you can nicely go to the next to leading order, and you can actually have this correction term here, where the C2 parameter extracted from data is always positive, which means that the higher spin states from this effective field theory picture has larger moment of inertia and also increases with spin. So the question then we set out to ask here, what does ab initio theory tell us about this? Can we reproduce this kind of features from a more like a, let's say, a fundamental description of nuclei? So we already heard in a couple of talks here about ab initio calculations of atomic nuclei. And I think if you ask different people, you will get a different answer, what they think or define as an ab initio approach to computing nuclei. We had a paper now with Andreas Ekström and collaborators a few years ago, 2 years ago now, where we put out our definition of what we mean or define as an ab initio approach to describe nuclei. And this is summarized in a sentence here, that we interpret the ab initio method to be a systematic, improvable approach for quantitatively describe nuclei using the finest resolution scale possible. All right, so what do we mean by that? So here you can look at the nucleus at different energy resolution scales, right? So you see nicely as you increase resolution, different degrees of freedom starts to appear and emerge, and finer details are resolved once you all get to high energy and you have quarks and gluons, right? So you might naively say this is the beginning, this is where we should start, but as we know, lattice QCD approach to describe nuclei are not very predictive at this moment, so we choose nucleons as the starting point for our approach and basically use effective field theory based on chiral effective field theory approaches to describe then different energy scales that appear from low energy collective motion to masses of nuclei, and also, as we'll hear in Francesca's talk, about response function and also towards quasi-elastic scattering of nuclei and neutrino scattering. So these are the kind of energy ranges from very few 100 keV to hundreds of MeV binding, and the challenge has really been trying to describe all these kind of different scales within a unified ab initio framework, and that's what I will try to convey to you in this talk, how we do this. I will not spend time on describing the input interactions. We've heard talks about this earlier today and also yesterday in Bira's talk. And we know there are problems regarding power counting schemes and what is the correct power counting and problems of normalization and using these interactions here. I will mostly not focus on the Hamiltonian here, but just take as input what we have available, this chiral effective theory, and solve the many-body Schrödinger equation. We know if we want to solve this exactly, this is an exponentially costly problem. So unless you want to just limit yourself to very light nuclei, you cannot do this. So we have to choose a different approach. Well, there might be hope one day that we can go to the right side here and use quantum computing to solve these exponentially hard problems. But I think we are still many years away from applying this to realistic nuclear physics problems. So we choose the route to the left here instead, using polynomial scaling methods such as couple cluster theory, IMSIG, Gorkov, self-consistent Green's function, and so on, which are systematically improvable approaches and also scale polynomial with the system size or the number of nucleons that you want to describe. Also, I'd like to discuss recent developments of emulators. So all these here require still high-performance computing facilities to solve at least heavy mass nuclei and deformed nuclei. And so there has been a lot of developments of emulator technology that takes these, emulates these high fidelity calculations at a much reduced cost, which allows you to perform millions of simulations on a workstation or laptop in order to perform some kind of statistical analysis and also sensitivity analysis of these kind of ab initio calculations. All right, so I'll next couple of slides here just give you an overview of the method of our choice, which is couple cluster. And it's basically what we call a single reference method. So you expand on top of some starting points. And as we know from effective field theory, you have to have a good starting point. Leading order should be a good approximation to your final solution. And so basically then we have a Hamiltonian, which consists of the intrinsic kinetic energy, 2 nucleon and 3 nucleon forces. I would like to emphasize that we do not include the full free-body force here. We use what is called as normal ordering approximation. So we can normal order the three-body with respect to some vacuum state, where we have a 0-body, 1-body, 2-body, and 3-body contribution. And we neglect what we call the residual 3-body parts, but we keep everything up to the 2-body normal order approximation here. This is then a normal order with respect to our vacuum states, right? As I mentioned, it should be a good leading order description. So for a spherical nucleus, you would assume that a spherical Hartree-Fock solution would be the best starting point. While if you go to the deformed system, like Neon 22 here, a spherical starting point is not obviously the most appropriate starting point. So we do a deformed. We allow for emergent breaking of symmetry and also break rotational symmetry here. And we start from a deformed Hartree-Fock state. And also we heard in Anna's talk before mine here about the Nielsen model. So basically here is showing you from oblate to prolate and the spherical limits here at 0 deformation. And basically this is our guiding point for setting up the best leading order description of a deformed or spherical system that we want to describe. So once we have defined the starting point, we include then what we call dynamical correlations here through a wave operator that induces many particle, many Hall excitations on top of this reference state. So I want to just briefly also mention some challenges here regarding including 3-body forces in these kind of deformed calculations. So this paper by Michael Frosini and Tomo Deghe and collaborators published a few years ago now emphasized the point when you normal order your Hamiltonian with respect to broken symmetry reference state, like a Hartree-Fock, deformed Hartree-Fock state, and you truncate the 3-body at 2-body approximation level, your Hamiltonian is no longer rotational invariant. So the way that they solved this problem was to basically first do a fractional filling in a spherical scheme where the orbits closest to the Fermi surface here are still treated within a spherical scheme, but we have a fractional occupation number for the orbits closest to the Fermi surface. Then you perform a spherical Hartree-Fock calculation, and then you normal order your Hamiltonian with respect to the spherical state, and this is the input then to the secondary deformed calculation, but now you have a Hamiltonian that is still rotational invariant. But I would like to emphasize here, when you go to very deformed nuclei, it's not really clear what is the correct filling of these orbits closest to the Fermi surface. So this is one of the challenges that we're dealing with in these kind of calculations here. So couple cluster theory basically, as I mentioned, we introduce this wave operator here that introduces what we call dynamical correlations on top of your reference state. These are particle hole excitations, typically truncated some low order. T1 is a 1 particle 1 hole, T2 is a 2 particle 2 hole, and so on. So this you typically truncate either at T2 or T3. And then we include what we call long-range correlations or static correlations, which comes from basically breaking and restoring symmetries in your wave function here. And we do this by what we call projection after variation techniques. So we have our couple cluster, broken symmetry states, which we then project onto good angular momentum here in this case. And basically we have to evaluate this kind of expectation value. And these corrections here from restoring broken symmetries are typically very small energy contributions if you're looking at the total energy budget, which you see here to the right. This is from the dynamical correlation from the first step. This is the correction from symmetry restoration. And you can see in this picture here, the contribution from restoring the symmetry is just a few MeV compared to 150 so MeV for neon 20 here in this case. So it's a very small correction, but it's also very important if you want to study or compute rotational structure, such as energy, rotational bands, and also transitions between these rotational states. Okay, so you might ask yourself, for those of you who are not experts in couple cluster theory, what is the convergence pattern of this expansion here, right? So we can analyze this by comparing it with exact calculation, the full CI, where you have now your exact wave function expanded in terms of particle hole up to a particle hole excitations, right? So if you include all these, this is an exact solution of your Hamiltonian for the A-body system. These are the shell model amplitudes, 1 particle 1 hole, 2 particle 2 hole, so on, all up to a particle A hole. These are the couple cluster amplitudes, as I mentioned, T1, T2, T3, T4, and so forth. So if you do CCSD, these are the terms that you include. So you can see that you already at CCSD level, couple cluster singles and doubles excitations, you basically include most of the correlations in the full CI wave function already. Now if you go to what is known as triples, you have exact up to 3 particle system, so the 3-body system exactly solvable, but you also see that you include terms up to a particle A hole, which comes from the exponentiation of this correlation operator. So this is really showing the power of couple cluster technique. So basically, even if you truncate at what we call T2 level, because we exponentiate this operator, we basically have all of these terms included all the way up to a particle A hole excitations in the system. So in the context of this conference series, you might ask if you want to describe something like an alpha cluster in nuclei, which is very collective kind of motion technique. We really would need to include up to full quadrupoles in this theory, which would also mean then including what we call T4 excitations. This is very costly numerically. It scales like what we call n to the 10th scaling here in system size, or occupied to the 4th, and occupied to the 6th power in the basis. So this is really heavy lifting, and we have not yet developed technology to deal with these kind of calculations yet. This is from quantum chemistry literature here, showing you the convergence pattern. This is different many-body methods, perturbation theory, couple cluster in green, and CI truncated on particle hole excitation level, and this is the excitation level of the theory. So you compare the same excitation level here. You can see the couple cluster theory, singles, doubles, triples, quadruples, very quickly recovers all of the full correlation energy in your exact wave function compared to other methods. We see similar patterns in nuclear physics. So this is from deformed neon isotopes. This is the Hartree-Fock energy. This is the couple cluster singles energy and doubles. And then this is the couple cluster singles, doubles, and triples. So again, as we see from quantum chemistry, the correlation energy from triples is about 10% of the CCSD correlation energy. We also looked at spherical nuclei from oxygen 16 all the way up to tin 100. And again, basically, if you look at this orange small contribution here, this is the triples contributions to the full energy budget. And for all of these spherical cases here, it's again about 10%. So we see a similar convergence pattern in atomic nuclei as you see in quantum chemistry applications. So now coming to the topic of this talk, more specifically here, looking at deformed nuclei. So we heard in Takashi's talk yesterday, right? There's a lot of excitement going around this exotic nucleus oxygen-28, which was discovered a couple of years ago now and published in Nature, as we heard about in yesterday's talk. And you might ask, what happens along this n=20 neutron number here towards this key nucleus here? And we know that this region here is a region of deformation, or this island of inversion. And basically we wanted to address what deformed couple cluster theory calculations tells us about, let's say, somehow the signature or the erosion of this n=20 magic number here towards oxygen-28, and also what we can say about this very neutron-rich neon isotopes here, where there's still data lacking for rotational states and transitions. So first we did a benchmark calculation to again assess the precision of our truncations and calculations here by comparing with symmetry-adapted Noether-Shell model. This is for neon-20, the 2+ 4+ state. The dashed line is the symmetry-adapted Noether-Shell model, and these are the couple cluster calculations for different model space sizes. And also we computed the BAV2 transitions from the 2+ to the ground state. The band here is the estimated uncertainty band from the symmetry-adapted Noether-Shell model. And these dashed lines here are different various model space sizes and frequencies of the underlying harmonic oscillator basis. And as you can see, we increased the model space. The dependence on the frequency of the basis becomes smaller, and we also nicely overlap with the more, let's say, more exact symmetry-adapted Noether-Shell model calculations using the same input interaction. So again, coming back to this question in the beginning here, this is also from the workshop a couple of weeks ago, where is the pairing gone? So it appears, if you look in the calcium isotopes, at specifically this pairing gap, the 3-point mass difference here, using different many-body methods and one particular interaction here, very few of them are able to describe this odd-even staggering effect here, which is associated with this pairing gap, which kind of indicates that these chiral interactions or many-body truncations that we impose on our theory is not appropriate to describing or incorporate the pairing effects in the specifically here in the calcium chain. We know from EDF calculation that this is the opposite effect here. So we have this Fajans functional, which actually where they made the point that in order to reproduce this parabolic trend of the radii, the isotope shift here between calcium-40 and calcium-48, and this very steep increase beyond calcium-48, you need to really include pairing correlations into your functional in order to have this trend correctly described. So the question is then, okay, you have pairing here, and then in our ab initio approach, we don't see any indication of the pairing effects. And we also computed the binding energy of calcium here using different truncations, couple cluster singles and doubles based on a deformed reference state. Well, we also have Bogoliubov couple cluster, which basically breaks particle number as a symmetry, and then you expand on top of a broken particle number reference state, Bogoliubov state, and include correlations in couple cluster. And you can see that all these methods here basically agree with each other, and again emphasizes that we don't see really the importance of including or breaking particle number, including superfluidity in the reference state is necessary to obtain good agreement here. So you might then ask yourself, what is the impact then on rotational spectra and transitions? So this is now the calculations for the 2+, 4+ states in neon-20 all the way through neon-34 to the drip line, and also for the BAV2 strength for the 2+ to the ground 0+ ground state. The black vertical bars here are experiment with experimental uncertainties for the transitions and also the excited states. And then we have different ensembles of interactions that we employed. And this is what we call the magic 1.8 2.0 interaction that has been employed widely in a community and is known to be very accurate in terms of describing spectra and binding energies. And again, you can see that we follow the data quite nicely all the way up to neon-34 here. And also for the BAV2 trend, you can see that we reproduce data quite nicely, or we follow the trend. And now the question, coming back to the role of pairing, right? So we know that this particular interaction here produces too small radii compared to data, right? So this would basically imply that the moment of inertia is too small, right? So based on the rigid rotor model, that means that we should have too large spacing of the rotation band compared to data. But we see that actually we have a nice agreement here with data. So what's going on? So might this be the fact that these chiral interactions induce so, well, little to almost no pairing in these calculations? And we know that the absence of superfluidity, which would increase moment of inertia, it's compensated by somehow accidentally by having too small radii. So this is an open question. And you can also see for this delta full interactions here, actually reproduce radii better than this 1.8. And you can see that we have a more compressed, slightly more compressed energy spectra than we have for the 1.8 2.0 interaction. So this might be an indication of this effect. We also looked at then the shape coexistence, right? So we move along the n equal 20. We know from experiment that magnesium-32 exhibits shape coexistence. There's a low-lying 0+ spherical band very close to the deformed ground state band that's been discovered. And you might ask, if you go remove 2 more protons moving towards oxygen 28, do you still see this effect? And then indeed, for neon 30, we do see the coexistence of both the spherical and the deformed shapes. This is for different Nmax truncations of the Hartree-Fock calculations and for different quadrupole constrained solutions of your reference state. Right, so as we increase Nmax here to our limit, which is Nmax 12, we can then take each of these points as our reference state and introduce this dynamic calculation through couple cluster. And increasing again Nmax, you can see that at our largest model space that we are able to perform, the deformed solution is indeed slightly lower than the spherical shape here for smaller quadrupole. Now we can then take the solution, project onto good angular momentum again to obtain the rotational band. This is what we obtain for the deformed configuration, and this is what we obtain for this low-lying spherical band here. Compared to data, you see that our rotational band is indeed quite nicely reproduced with what is known from data. Still needs to be known or experimentally investigated whether indeed there is also this low-lying, more spherical configuration that exists at low excitation. We also move to very heavier, strongly deformed nuclei. Here we move to the proton side of the nuclear chart, specifically looking at zirconium-80. Right, so this is n equals c equal 40 shell closure. Naively in the harmonic oscillator, we would think this is a spherical nucleus, but we know from both experiment and also from this mean field or beyond mean field calculations here by Thomas Rodriguez about a decade ago or so now that this is much more complicated story. And they found here in these calculations coexistence of very different shape from oblate to prolate deformation. And the question is then, what do we find in our calculations? And indeed, what we see here is a very complicated structure. We have oblate, spherical, prolate, and more largely prolate deformed shapes at the constrained, quadrupole constrained Hartree-Fock level. We can then take each of these reference states, include couple cluster correlations with estimated uncertainties coming from neglected triples, and also adding onto that corrections from symmetry projections. And these are the uncertainties that we estimate. And this is experimental binding energy here. So you can see that we agree fairly well with the binding energy, but we cannot unambiguously say what is the ground state shape, because you see all of these within uncertainties overlap with each other. So still a challenge to say what is the ground state of, shape of zirconium-80. Now we could try to look in more detail by looking at the spectra and the BeV2 trends of nuclei in this region here. So this is for zirconium-80, comparing the rotational band experiment to the left, couple cluster for what we call the prolate, which is taking this configuration, and the larger prolate, which has larger quadrupolar deformation, projecting onto good angular momentum, This is the spectra that we obtain. Right, so we see now that indeed we don't get this rotational stretching of the higher spin states, as we find, as I introduced in the second slide. Right, so we have a two compressed spectra compared to the data. Maybe the larger prolet is a better agreement, and then we also compare to other mean field, existing mean field and beyond mean field calculations here. I would say for the larger prolet, we fairly good agreement with existing theory and also with data. But then looking at the BAV2, for example, this is zirconium 80 here. This is the data. This is the BAV2 for this prolet configuration, and agrees well with data, while for the larger prolet, we get a too large BAV2. Right? So we cannot really, based on these two properties, again, say what is the preferred configuration of the ground state, either prolet or larger prolets. So these are still open problems that really challenges this ab initio approach to describing these properties. Then we went to also 5 minutes, okay. So we went to the other side of the nuclear chart, looking at deformation in nickel 78, right? So this is a Nature paper from 2019 here, where they found this very interesting structure of this nucleus. This is a low-lying 2+ state that's close to the spherical 2+ state, which they presumably assumed was part of a rotational band, but they did not see the band head, the 0+ state. Then you have this Monte Carlo shell model and large-scale shell model calculations that indeed, in their modeling, found this 2+ state being part of a rotational band close to the ground state of nickel 78. So again, now we did calculations here, couple cluster theory from nickel 78 towards calcium 70 for different, again, quadruple constrained Hartree-Fock solutions, and adding correlations from couple cluster theory. We have a good agreement with the binding energy of 78, and also from this is the mass table extrapolation here, and our calculations overlap within uncertainties. And then these are predictions here for chromium 74, titanium 72, and calcium 70. So interesting, you can see as we move towards calcium 70, the potential energy surface starts to flatten, which indicates more complicated structure here. So there will be more mixing between different references with different shapes. And our technology at the moment does not allow for this kind of generator coordinate methods that would allow for mixing of different shapes in this nucleus. So still a challenge describing nuclei here. This is the spectra that we obtained for nickel 78. This is what we published some time ago now using the spherical couple cluster theory. Experiment is to the right here, and this is what we get now in the deformed approach. So we indeed find also a low-lying rotational band. Uncertainties are still quite large, so we go from nmax 10 to nmax 12 here. You can see that it moves down quite a bit, but the spacing between these states are similar to what is seen in Monte Carlo shell model and also large-scale shell model. We also did excited states from iron, chromium, and titanium, comparing to other existing calculations here. This is the valence-based DMRG, which is the IMSG-based approach. This is a large-scale shell model, and the takeaway here is that we largely agree within uncertainties with the large-scale shell model approach, while the IMSG approach seems to be less accurate in describing this kind of deformed configurations. So in the last, what do I have? 2 minutes, 3 minutes? 5 minutes, okay. So in the last part, I would like to also address a question that we have tried to answer, or shine some light on, is to ask what drives deformation in nuclei. We know from a long history of phenomenology here from back from the 50s, explaining how deformation emerges in different models. We have Bohr-Mottelson model. We have also computation between pairing and quadrupole interactions from HFV. In the 70s, we have the isoscalar neutron-proton interactions dominating over isobacter pairing from a shell model, and so on. So the question we would like to answer, how can we understand the emergence of deformation from the underlying interactions that we employ? And specifically, how sensitive is deformation to variations of these low energy constants that we have in this chiral effective field theory approach to describe nuclei. So the basic tool is what we call global sensitivity analysis. So basically you have your chiral EFT model with a specific number of parameters. And so you squeeze your model then in a specific way, and you see how this impacts specific observables such as BeV2s or 4+ to 2+ energy ratios for deformed nuclei. And this kind of then will tell you in some way how specific parameters of your model impact these observables. This is really it has been, well, up until recently, really a bottleneck, because this kind of analysis typically requires millions of model evaluations to really have to perform this kind of sensitivity analysis. And we basically, well, with Andreas, we set out to solve this using argumentative continuation techniques based on the work of Dylan Frame and also by Sebastian Koenig, who applied this in a nuclear-ladder CFT approach and also a Noko shell model of light nuclei. And we generalized this approach for couple cluster theory. Basically, the main difference is that in couple cluster theory, the Hamiltonian is no longer Hermitian, so you have to solve for right and left states. So this is your parameter domain here. You pick what we call snapshots or training points, where you solve the exact couple cluster solution. And then you project your Hamiltonian onto this small subspace of exact solutions, and you have some specific target value for the Lorentz constants, which you then evaluate by diagonalizing basically a small, let's say 10 by 10 matrix, instead of using supercomputing resources to solve the exact solution. Just to show you how it works, this is varying the signet S contact. And these are exact calculations for singles and doubles for the binding energy and the radius of oxygen 16. Now we vary this constant here in a very large range. So these are exact calculations. Now we add 2 training points, snapshots. We diagonalize then 2 by 2 matrix for all of these target values of the Hamiltonian. And you can see for binding energy, not too bad. Radii, okay, less good. Okay, we add another point, so we have 3 by 3 matrix. We diagonalize, better, 4 by 4, 5 by 5. Basically, we reproduce both binding energy and charge radius within this whole range of the Lorentz constant. We can also do the same for rotational states. This is, again, the same coupling here in this large range. This is the training region that we obtain, so these are the snapshots. We have exact calculations for these points. And then comparing the exact, which are these filled symbols, with the subspace projected results, which are the dashed line. You can see again that we reproduce basically the 2+ and the 4+ rotational states in this whole range. This is the 4+ to 2+ energy ratio, which is again a measure of deformation, right? So we know the rigid rotor limit is here. And you can see now as we vary this constant here, which is again signature of this isovector spin singlet pairing in nuclei, right? So this is basically driven by this partial wave. You can see as we increase this, it impacts deformation quite significantly for looking at this 4+ to 2+ energy ratio. This is showing you in real time now, using the subspace couple cluster calculations of charge radii and ground state energy evaluations of oxygen 16. Right, so the accuracy of these, let's say, emulations here are roughly the size of the pixel size. And the speed up is really tremendous here, right? So 20 years of single node computations can now be replaced by 1 hour run on a standard laptop, which then allows us really to perform this kind of simulations or sensitivity analysis that we see here. So in 5 minutes here, we have 10 to the 5 energy and radii evaluations. So then, performing the same kind of, well, sensitivity analysis for deformation. This is summarized here. These are then the R4, what we call R4 two main effects. These are the Lorentz constants of your next to leading order Hamiltonian. These are the pion exchange. These are the short range contact parameters. This is the 3 nuclear force contact parameters here. And what we see strikingly is that the singlet S contact here dominantly impacts, is mostly sensitive to deformation, or specifically this 4+ to the 2+ energy ratio. So we tried to have some interpretation of this, right? So we see that 50% of deformation is driven by the signet S contact. And presumably is that adding the short-range repulsion here, as we also saw in this figure here, right? So this basically this parameter by, increasing, basically, presumably by reducing the pairing effects, that increases deformation effects. We also see that the pi-nucleon constants here has some impact, and presumably it is by adding attraction in higher partial waves. So it's still, I mean, say it's a first step towards trying to link deformation to the underlying Hamiltonians that we employ from chiral effective field theory. There's still a lot of work to be done here, but I would say it's just the first step, trying to understand it on a more fundamental level. So with that, I will thank you for your attention and just leave the summary up here for you to read.
So thank you very much, Gaute, for a nice talk. Carlos has a question. Yeah, try to shout, I think it's fine.
So, Gaute, as you know, the best measure of pairing we have is this delta 3 function, right? Which is this separation energy measure. And when I was in Oak Ridge with you, a long time ago, we spent a year working with Birch, running HFB.
Mm-hmm.
And when you say Fayence density functional, for pairing, the only thing which matters is the pairing term, which is phenomenological. Any density functional, you add a volume pairing, surface pairing, mixed pairing, and it's very unpleasant. Density functional is pleasant. The pairing term is unpleasant. We ran 800 nuclei, and we got in the end that the RMS compared to experiment, the best was the Weizsäcker formula. This term 11 over mass A to 1/3 MeV. It has a smaller RMS than this density functional as the pairing term. So now my hope is, you cannot do this with the odd nuclei, but my hope would be to understand pairing from first principles. Like you could do this ab initio and test the thing and see what the hell is pairing. Nobody really knows. You know, people say, well, it's two magnets, it's all BS, because in the end it's phenomenological. But if you could do this for us, this would be a great thing. So how far are you to extend this to odd nuclei and then give us the answer?
Well, so what I showed was for the calcium, so we can do the same kind of analysis for other isotopic chain. But I think calcium is like triple challenge for us because this has this parabolic arc in which the Fajans explains from pairing, right, in the EDF sense, but we do not see that. And then the pairing gap, the 3-point mass difference, right, which is also has been interpreted as a sign of pairing. So there's a lot of different quantities you have to compute. Maybe I'll go back.
So you don't put any phenomenological pairing, you just do with the nuclear-nuclear interaction.
Yeah, so there's many different quantities, right, which has been interpreted of signature of pairing here, right? But so I would say interestingly, right, so I didn't go into much detail here, but this is data, you see, it's a busy plot. And one calculation that actually reproduces the data quite well here is the IMSG calculations where you break up the calcium 40 core and you do silicon 28 as a core. So you have a larger valence space, and they do IMSG2. But then if they go to the next correction, which is including some leading order 3-body terms in the IMSG3, you go from reproducing data back to not reproducing data. It's difficult to see here. This is this. difficult to see. It's this brown here, right? So you go back here. But then for this parabolic trend, none of these calculations reproduces the parabolic trend of the charge radii isotope shift. Even if you reproduce the 3-point mass difference here.
What
So-
do you think is the reason?
Sorry, then.
What do you think is the reason?
What's missing?
Yeah, is the interaction, is some,
I don't think it's interaction. I think it's many-body truncations here. There is some evidence of traxial deformation in mid-calcium isotopes here, which most of these methods cannot appropriately take into account. That could be something. There could be some mixing of different quadrupole fluctuations here going on, which is difficult to include in these calculations. So my guess would be it's a many-body truncation error. Because we looked at this for many different interactions and we see the same trend.
Okay. Any other question for Gaute? Yes, Daniel?
Thanks for the nice results. Can you show the results where you were trying to discern the ground state of, I think it was the zirconium? And you commented that you couldn't tell what the ground state was within the uncertainty of adding triples. This one, yeah. So by now you probably know how correlated the triples correction is across different shapes. So how correlated is the triples correction when you apply it for different ground state shapes?
Correlate, you mean what types
like
of...
does it, so okay, what am I trying to say? So if I do the triples correction for a bunch of different shapes, do I tend to get similar numbers or do I get completely random numbers?
You still get the 10% correction typically.
But is it, is like, some of them are up and some of them are down, or are they all in the same?
Or they're still adding binding energy correction, yeah.
Right, so then I would suggest that all your your error bars here have to be interpreted as highly correlated.
Yes.
And therefore, you may well be able to tell what the ground state is, because if you take differences, the correlated errors will disappear.
True. Yeah.
Okay, very good. I think we can leave the other questions for the afternoon session. Let's thank Gaute again. And next talk is going to be given by Francesca Bonaiti on